Welcome to another session of mixed signal IC design, and we are discussing about digital to analog converters. So far we covered resistor R to R DAC and the other type of DAC. So if you look at the initial discussion where we have mentioned about the ways the reference voltage is generated, uh, we mentioned about three different ways. One is based on voltage, from a voltage using a voltage division using a resistor ladder network or a resistor string. We looked at two types of architectures of DAC. The second thing is based on current. So that preliminary discussion we have done before. We take a reference current, and the reference current will be divided into there are two ways basically. We can use a reference current and we can divide that into n equal currents using n identical switches, or it could be in terms of binary current division. You can see both the pictures on the screen. We'll be using equal currents in all the branches, or we can go for binary current division. So here today what we are going to discuss is about current steering DAC, where we use current sources to steer and finally convert digital voltage into an analog voltage, right? So for that reason we call it as current steering DAC. Again, how we are controlling the digital switches, whether it is using a thermometer code or it is using a normal binary code, depending on that we have two types of architecture. So in general we call this as current steering DAC. So to start with, the one important thing of this current steering DAC is here we uses current throughout the conversion. Current is used instead of talking about voltages. We talk about current, or current is used throughout the conversion process. And one important requirement of this DAC architecture is we need to have very precise current sources, because the data, the conversion from digital to analog, since it is happening based on current source, we need very precise current sources in this case. So that is another requirement of this. So what we need is here precise current sources. Current sources are required. And now how we use this current sources to generate the required voltage? There are two methods, or at least we will discuss two different ways of using this current steering DAC. First, let us go with a generic architecture. When I say generic architecture, here basically the difference is how we are controlling the switches in order to get the current. Now the first one what we are discussing now is called a generic current steering DAC, where we use a thermometer code in order to control the digital switches. We'll see how it is. So if you look at the typical or the generic architecture of this, as I mentioned, we'll be using current throughout the conversion, and in this generic architecture we'll be using a set of current sources having equal value. So say for example, let me consider a 3-bit DAC. So when I say 3-bit DAC, so for a 3-bit DAC, we know the digital input codes will vary from 0, 0, 0 all the way up to 1, 1, 1, right? So if you look at, so one thing we know, when the digital input code is 0, 0, 0, we will not expect any current to flow. That means there is no current source required for this. No current source required. Now when the input code is 001 all the way 010, 011, then 100, 101, 110 and 111. These are the different input combinations. So what I need to know is, for every input digital code, how I am converting or how I am getting analog quantity at the output, and in this case the analog quantity is a current. So look at this from here, from starting from this input digital code till 111, we need current sources, right? From 001 up to 111, we need current sources. So for a 3-bit, if I look for a 3-bit DAC, how many current sources are required? In this case, in the initial, since the first data is 000, no current source. So for the rest, all the 7 combinations, for all 7 digital input combinations, we need current sources. So for a 3-bit DAC, we need 7 current sources. I'll come to the architecture. I'm just looking at, taking an example and looking at the number of current sources which are required. So 7 current sources are required in this case. Now, in that case, when you have 7 current sources, like we'll have 7 switches to control all these current sources. So switches can be numbered from 0 to 6. Yeah, we'll see how it is. And so in general, for a n-bit DAC, we need, how many current sources are required? For a 3-bit, we need 7. So for an n-bit DAC, we can say we need 2 to the power of n minus 1 current sources are required. Alright, so for a 3-bit DAC, we need 7 current sources. That is how the architecture is. Now let us see the generic form, how it is. So let me draw for a 3-bit DAC. So a 3-bit generic current steering DAC. So we need 7 current sources. So this is 1, 2, 3, 4, 6 and 7. These are the 7 current sources what we have. And let me connect all these things, and this will be this point I am connecting to ground. So what we know is, depending on the digital input data, the current sources has to steer the current, and corresponding data will be available at the output. So I am considering all are equal current sources. All are of current source value is I. Now, depending on the input digital data, we need to get the current, right? So let me so the current need to be steered, either the current source should be connected to either the switch, because we have the input digital data, so either the switch should be connected to ground or the switch should be connected to the current source. So that is what we know. So this is how I am connecting. Right. So let me draw the current direction as this. Now if you look at this, here we have many switches. So let me number the switch here from, this is D0, this is D1, D2, this is D3, D4, D5 and D6. So there are 7 switches. For every input digital data, we should, like, every input digital data is controlled through the switches, and the current will be routed to the output point, right? So what we can see here is, we have a set of current source having unit value or equal value. Say I'm assuming it as I could be any current depending on the requirement. And when all the inputs are 0, our requirement is there is no current source, or there is no we don't need any current. So basically what I need is current is 0. Yeah, I out will be equal to 0. Yes, Pratap. So if I'm connecting all the see, when the digital input data is 0, all the current sources are connected to ground, and there is no current. I out is basically 0. Now depending on my input digital data, so what it happens here is, when the digital input data is 0, 0, 0, all the switches, the connection of the switch is from D6 all the way up to D0. One second. Yeah. Let me write it here. Give me a second. All right. So let us look at how this works. So let me write the digital input code here, which varies from 000. All right, this is the digital input code, and depending on this, depending on the digital input code, what I need is an output current, right? So as input binary data changes from 000 to 111, what we expect is equal increment of current. So in this case, if it is I, for every input change from when the input changes from 000 to 001, what I expect is one increment. Increment will be the LSB, one LSB value. So that depends on the unit current value what I choose. Now look at the switches which control. So how many switches we have? We have switches from D0, D1, D2, D3, D4, D5 and D6, right? So initially all the switches are connected to ground, or all the switches are off. When the switches are off, it is connected to ground, and the expected output current is also 0. Now when the digital input code is 001, what I expect is I need unit current. So I say for example I is a current flowing through this. So when the digital input data is 001, what we use here is a thermometer based code. So the first switch will be on, this is 1, and rest all will be equal to 0. So rest all the switches from D1 to D6 will be connected to ground, but the first switch, the D0 switch, will be connected to the current source, and the current I out current will be equal to I. Similarly, for the second, when the digital input code changes from 001 to 010, what happens here is, because here we have the input as the binary data, but the switches need to be controlled in the form of this, in form of this fashion, as we have unit current source here. So here for this we will have two, because what I need is when the input data changes from 001 to 010, I need one more increment. For one more increment, I need to have this kind of setup here, and for this we will get 2i. Similarly, for the next one, we'll have 3 switches turned on, then we'll have 3i, then we'll have 4 switches turned on, for that we'll have 4i, then we'll have 5 switches turned on, that we'll have 5i as the output current, then the 6 switches turned on, and finally all the switches will turn on, and that will corresponds to the 7i current what we have. All right, so this is how a normal this is how a normal generic current steering DAC works. And when I say generic current steering DAC, the input or the input code here is thermometer code. That is, an encoder is required in this case, and here we have unit current. All the current sources are equal. All right, so the output current. So in this case, the output current I out will range from 0 to the maximum current. In this case, is 2 raised to n minus 1 times I. Right. So this is one way. As I was mentioning, there are two ways we can go. The thermometer code based or the generic current steering DAC works in this way. Right. So since the number of current sources required is 2 raised to n minus 1 into I, the digital input cannot be the normal binary form. It should be in the form of thermometer code. And depending on like which bit is, so which depending on from LSB to MSB, depending on which digital input code is there, all those bits will be high and the rest will be 0, as you can see the connection of the switches over here. All right. So now, in the similar way, whatever we have seen as current steering DAC with the help of thermometer code, the same we can also generate, or we can have another structure here with the help of a binary weighted current steering DAC. So that also we will see how it is. I hope this part is clear. If you have any questions, please put it in the chat box. Yeah. Now let us look at the binary weighted current steering DAC. So here, so when, as the name suggests, since the DAC is binary weighted, what we have is, in the previous case we were for an n-bit DAC we were using 2 to the power of n minus 1 current sources, but here this type of DAC requires only n current sources. But the difference is, in the case of this one, generic current steering DAC, we were using 2 to the power of n minus 1 unit current sources. We need a huge number of current sources, but all the current sources were equal, the values were equal. But here in binary weighted current steering DAC, here we need only n current sources. For an n-bit DAC we need only n current sources, but of various sizes. Right. And for that reason, since we are using binary weighted current sources, the input can be, the input code can be binary data. Thermometer coding is not required. Input code can be of binary data. Alright, so just to have a idea about this, what we'll use here is, maybe I'll just draw a generic structure. This will be the connected to ground, and so now I'm just drawing a generic structure. So since it is a binary weighted current steering DAC, the first current source, if it is I, the second one will be 2I, third one will be 2 square, which is 4I, and finally the last one will be 2 to the power of n minus 1 into I. Right. Say for example, if we need a 3-bit DAC, 3-bit binary weighted current steering DAC, the number of current sources what we need is also 3. Which are the 3 current sources? One is I, another one is 2I, and another one is 4I. Right. So which is 2 to the power of n minus 1 into I. This is how we draw a generic structure. Alright. Now the advantage of these kind of DACs, the advantage of either a current steering DAC or a binary weighted DAC is, which can, since it is having a high current drive, it is also used for high speed applications. Now we can have a basic comparison between these two types of DAC, whether it is binary weighted DAC or the generic thermometer code based DAC. So depending on the resolution, depending on the number of bits what we go for, because in the case of both have its own challenges. See, in the case of binary weighted, the number of current sources are required is small compared to the generic current steering one, because there we need 2 to the power of n minus 1 current sources, but here the current sources requirement is n. So thereby we can see that there is a huge difference in the area what we have in the current source. But at the same time, in the case of the generic current steering DAC, we need only if we design a unit current source, we can actually replicate that, the same design, and definitely there will be mismatches. We need to consider mismatch errors in a separate heading. But the requirement is like huge number, but one accurate current source can be replicated there. But here in the case of binary weighted DAC, the size has come down, or the number of current source requirement has come down, but we need binary weighted one, right? So if we have I, then we need 2i, 4i, and depending on the number of bits or depending on the resolution, we'll have like large current requirements as well, right? So anyway, I hope you understood the two generic structure. We'll go to some specific problems and we'll see how we can design this. I hope these two architectures are clear. If it is clear, can I get some response in the chat? All right. In that case, yeah. So let us just design this DAC. The question is design a 3-bit current steering DAC using the generic current steering DAC. So when I say the generic current steering DAC, the meaning is you need to use the thermometer code based one. Assume that the input current source is 5 microamps and the total output current, so we need to find the total output current for each input code. So the requirement is a 3-bit current steering DAC. So since it is generic current steering DAC, since n is equal to 3, so how many current sources are required in this case? We need 2 to the power of n minus 1 current sources. We need 2 to the power of n minus 1 current sources. That means 7 current sources are required. Right. So you can draw the architecture as same as before what we have done. Maybe you can present the data in the form of a table as digital input data, which varies from 0, 0, 0 all the way up to 1, 1, 1. Alright, this is the digital input data, and the input, since it is a generic current steering DAC, you can also write the thermometer code based input data. You have 7 current sources, so you need 7 switches, and the switches can be numbered from D0 up to D6, and this is D6. And for each for every input digital data, depending on the thermometer code, we'll have the output current. So initially all the switches are 0, output is also 0, we are not expecting any current. Now the unit current value is given as 5 micro, so initially when this is 1, the current will be 5 microamps. Then when this becomes 1 and 1, again assuming no mismatch, what we have is 5 plus 5, 10. Similarly, we can write up to all ones. So this is 15. This is 20 microamps. (25). This is 30 microamps, and finally when all ones, it is 35 microamps. This is how we present the data, the output current as well as the digital input data based on a thermometer digital input data. Alright, so I hope this part is easy comparatively, because we are not doing any other assuming a current source value, we are actually, depending on the input digit later, we are looking at the increment in the output, right? So let us now see, now understand the mismatches in this current steering DAC. So yeah, so when we study mismatch errors, first we will study based on the thermometer code based current steering DAC. Both are slightly different. So first let us look at the thermometer code based current steering DAC architecture and the mismatch errors which can come in that. And so basically why we are looking for mismatch errors is based on that only we will be able to specify or based on that we will be able to tell about the non-linearity, whether it is DNL or INL. All right, so let us look at this mismatch errors. I hope the previous part, even the binary weighted part, is clear. So let me consider, we have various current sources, right? We have for n bit DAC we have 2 to the power of n minus 1 current source, but the unit value we are looking for a same value current source. So let me write each current source is, if I am writing it as kth current source ik, we'll have the unit value, a unit current value I, plus I am assuming mismatch, which is written as delta ik. It's small change in the current value for the kth bit, and we know that this k can vary from 1, 2, 3 up to the power of n minus 1, because that many current sources we have. All right, so where this I is the ideal value, and what we write this as delta ik is the error due to mismatch. All right, so our intention is to come up with the expressions for DNL and INL, and to also to mention that for a n bit DAC, for a DAC to be n bit accurate, the DNL and INL should be half of the LSB, or it should not be more than half of the LSB, right? Now, if you remember, in the case of the previous R2R DAC or the resistor string DAC, while discussing about mismatch errors, we come up with certain assumptions, right? Based on one of those conditionally, we derived the mismatch error. So, in a similar way here also, we are actually assuming that. So, one assumption what we are making is the sum of all the mismatch errors, that is delta ik, the sum of all these things we are equating to 0. So how we are equating this as 0 is by mentioning that, see, if we have 2 to the power of n minus 1 current sources, one half of the current sources we assume that it will contain maximum positive mismatch, and the other half contains maximum negative mismatch, or the vice versa. And in order to get the worst case condition, so if I say that one half will have maximum positive mismatch and another half will have maximum negative mismatch, the worst case, when we look for the worst case mismatch, and thereby when we write the worst case INL or DNL, it will actually come occur at the mid range, right? Because if I have, say, if I have current sources from 1, 2 up to 2 to the power of n minus 1, and if I say that one half will have maximum positive, another half will have maximum negative, then the worst case INL will be somewhere in the mid, not somewhere in the mid, it is actually in the mid scale, right? So keeping that in mind, and with the assumption that the sum of all the mismatches will be equal to 0, if I write the output current I out, I can write output current as summation this value from 1 to the number of current sources what we have. Now since we assume that, okay, let me just write that over here. I'll take that delta ik is equal to 0, and also I'll also say mention that one half of current source, contain maximum positive mismatch, and the other half maximum negative mismatch, right? So some delta I max here positive, and this is minus delta I max. So if this is the case, if I am considering this as one case to study about the mismatch errors, then I can say the worst case condition, will occur at mid scale, mid range, right? All right. So now I am going to write. I am writing the worst case mismatch. So based on the worst case mismatch, if I can write that I out will be equal to summation k is equal to 1. So no need to go till the last value, because the maximum or the worst case mismatch is in the mid. So I'll write up to 2 to the power of n minus 1 over here, I plus delta ik. Right. So the calculation or the mismatch error discussion is based on the condition that one half will have positive mismatch and another half will have negative mismatch. So this can be further written as 2 to the power of n minus 1 into I, which is actually the ideal what we expect, plus 2 to the power of n minus 1 into the mismatch term. So the mismatch term I will write it as delta I, and this is the maximum value, delta I put the maximum by in order to mention that this is the worst case, right? So I can write this as I out is equal to this 2 to the power of n minus 1 into I is the ideal value. So this is the I which is ideal, plus 2 to the power of n minus 1 into delta I, this is the mismatch, and the maximum occurs at the mid scale. Now if I want to just write the INL, so if I write the worst case INL in this case, we know that worst case INL or INL is simply the actual output current minus the ideal one. So the actual output current is this, what you can see, this is the actual one, and the ideal is this quantity what I have. So actual itself can be written as ideal plus the mismatch error. So when I write worst case INL by subtracting actual from ideal, I can write this as 2 to the power of n minus 1 into delta I max. I hope this is clear what I am writing. If you have any questions, please put it in the chat box. So let me write this as actual. Right. So the worst case INL can be written as 2 to the power of n minus 1 into delta I max, and this is the maximum INL. So what we are seeing here, this quantity is basically the mismatch error in the current source. Or I should say maximum mismatch in the current source. Now all these things are based on the assumption or the condition what I have mentioned in the beginning, right? Now so what we always look for is after talking about the worst case INL, how we can relate this with the number of bits or the resolution, right? So let me look at this. So we know that for a generic current steering DAC or for a binary weighted current steering DAC, every current source represent one LSB, right? Because now in the case of we are discussing about current steering DAC, so here every current source represents one LSB. So one LSB can be equated to the unit current source value. So in that case, if I want to mention about the worst case INL, we always say that the worst case INL should be within plus or minus half LSB. So half LSB can be written as half of the current source value. Alright, I hope this you are understanding this. For every DAC we talk about one LSB, the least the significant bit, right? So the minimum resolvable voltage or the current. So in this case, one LSB is equal to the unit current source value. So half LSB is equal to I by 2. Now, um, we know that maximum INL should be equal to plus or minus half LSB. That means delta I, the maximum value of this, should be equal to half of LSB. From the previous expression, we wrote it as delta I max NL. What we wrote it as half of LSB. So that can be written as, let me first write this as 1 by 2 to the power of n minus 1. From the previous expression I am writing, from this expression I am writing worst case INL. So worst case INL is half LSB. So half LSB divided by 2 to the power of n minus 1 can be written as delta I max INL, right? Or if I write this further, I can say delta I max INL can be written as half of LSB is nothing but I by 2. So I by 2 into 2 to the power of n minus 1, which is equal to I by 2 to the power of n. Right. So the maximum mismatch is equal to I by 2 to, so delta I max INL is equal to I by 2 to the power of n. So let me just write this here. I by 2 to the power of n. Right. So what is the significance of this discussion, what we made here? So we spoke about thermometer based current steering DAC, and then we based on the assumption we arrived at the worst case INL value. Now what is significance of this? So does it talks about the difficulty of using this architecture for high resolution? Say for example, let me just take this example. Say I am looking for a 12-bit DAC, and what I have as the unit current source value is the as same as the previous example. I have a 5 microamps current source, right? Now based on the discussion what we made here, based on that, the worst case INL, what we know is half of LSB, that is half of LSB error. So what can be delta I max for this case? So the delta I max for this case can be equal to I by 2 to the power of n. So I by 2 to the power of n is actually 5 microamps divided by 2 to the power of 12. If I get to the value of this, it is very close to 1.221 nanoamps. This is very, very small, right? So the maximum mismatch error, or the maximum mismatch error, or the mismatch in the current can be 1.221 nanoamps. That means the difficulty here is, since this is the mismatch error, when I look for a 5 microamps current, the mismatch or the due to all the errors, this current can go all the way up to 4.998 microamps or up to 5.001 microamps. Even though we are looking for a 5 microamps current, we know that there will be mismatches, and based on this calculation, or based on this worst case INL scenario, this current should be in this range, right? So to achieve in order to achieve a worst case INL within half LSB error is actually challenging, especially when we look for a current source of 5 microamps, and that error should be within 1.221 nanoamps. So there is definitely a difficulty in using this architecture, and or this shows that use of this architecture for high resolutions is challenging. So generally, so what we are discussing is current steering DAC based on thermometer coding. There is one more, as we discussed, binary weighted is also there. So generally, maybe by this time you understood that there are the two varieties, and both will have its own disadvantages. So people use something called a segmented DAC, where we use thermometer based coding up to one point, and then we use binary weighted. We use a combination of these two. So after discussing binary weighted, we'll come to that. Alright. So I hope this discussion based on INL is clear. Maybe let us solve. Second. Yeah. Let us solve one question, and then we'll come to the DNL, or let me discuss DNL also. Then we can come back to a numerical. I hope you guys are with me. Can I get some response in the chat? Alright, so let us look at DNL also. What is DNL? DNL is the maximum difference between two adjacent values of the output, right? So previously we were looking at the output voltage, but now so DNL is the maximum difference between two adjacent values of current. Right. So how I can write it is output at a specific value, say at x minus the output current of the previous position. So if I am considering x, then the x minus 1 position or x plus 1 position, that difference. How can I write that? I can write this as the current value, the difference current value is, I can write it as ik plus the delta I max, which is the mismatch error. So I'm just writing it as delta I max of DNL. So this can give the maximum DNL. So the DNL max can be written as Ik plus delta I max of DNL. This is for a one position. So this minus the previous one, which is Ik. So that can be written as delta I max of DNL. Now from the previous discussion, we know that the maximum DNL can be half of LSB. So half of LSB is nothing but I by 2. So this is equal to delta I max of DNL. This is the maximum mismatch what we can have for the DNL. So in the DNL calculation of the delta I max, the maximum mismatch error can be I by 2. Alright. So are there any questions based on this DNL and INL calculation? So let's look at this numerical. And the question is, a certain process is able to fabricate matched current sources to within 0.05%. The question is, determine the maximum resolution that a current steering DAC can attain using this process. It is given that it is non-binary weighted, so it is thermometer code based one. So we need to find the maximum resolution current steering DAC can attain using this process when we have current sources within the mismatch error as 0.05%. Alright, so how will you start? We have certain equations what we have written, right? So we know that delta I max of INL, what we have written is, it is I divided by 2 to the power of n. And delta I max of DNL is written as I by 2. Now when we write delta I max of INL and delta I max of DNL, these two things basically represents the current source mismatch error, right? So these two things are mismatch errors, maximum mismatch errors. These two things are mismatch errors. And we also know that the mismatch errors in INL and DNL should be within 0.5 LSB. That is how we generally define an n-bit accurate DAC, right? So if I look at these two things, these two are basically the conditions for the mismatch error, the maximum mismatch error for INL and DNL. And if I look at this, we can say that clearly the limiting factor is INL, not DNL. The limiting factor is basically INL. So this is the limiting factor because the maximum INL is I by 2 to the power of n, right? So depending on the mismatch error given in the question, I can write that since the delta I max represents the mismatch error, it is given that it is up to 0.05 percentage of the current value, the I value, right? So delta I max is I divided by 2 to the power of n, that can be equated to 0.05 percentage of I, or from this I can write that 2 to the power of n is equal to 1 divided by 0.05 percentage, so it is 0.0005. Alright, so when you calculate from this, what is the n value you are getting? I think you will get, yeah, if you have answers you can just tell me. The n value somewhere around 10.97 or something. Yeah. So yeah, so it is 10.97. So when we talk with respect to the mismatch errors, yeah, we'll take the minimum value up to 10. So the resolution, the maximum resolution what we can get is only up to 10. We cannot get 11, right, with this mismatch error. All right. So we discussed about current steering DAC. We started with the generic one. We also looked at the structure of a binary weighted one. Then we saw the mismatch errors in current steering DAC based on the thermometer code base. The other one, the binary weighted mismatch errors, we will deal in the next class. All right. So if we have any questions, we can discuss now.